So, yesterday we introduced the method of partial fractions. So today we're going to do more partial fractions. And whereas yesterday I just showed you a couple of examples how we actually use it, today I want to do it a little more formally. Not as formal as it could be, but a little more formally. Just to see how far we can push the method. Okay, and under what circumstances we should be attempting the method. So the first situation is going to be the following. We're going to be looking at functions that look like a polynomial divided by a polynomial. Okay. It's going to look like P of x divided by Q of x. Okay. Well, it'll actually always be this case. But in the first case, my Q of x is going to look like the following. So, by the way, these are all, I should say, these are polynomials. Okay, so remember, polynomials, x cubed minus 14x squared plus 2/3 x minus 6. Okay, there's no signs showing up, no exponential functions, nothing nasty. You don't have quotients of polynomials, right? It's just a straight polynomial. Okay, so you have a polynomial divided by a polynomial. And I want my Q of x to look like the following. It's going to have a linear term, right? So linear means degree 1. Okay, so remember the degree of a polynomial is the highest power of x that you see. Right? Just like, remember the order of a differential equation was the highest derivative you find? Well, the degree of a polynomial is the highest power of x. Okay, so this has power 1. That's the highest power of x. So this is a first degree polynomial. Okay, and first degree polynomials are also called linear polynomials. Well, I don't want Q of x just to be linear. I actually want it to be a product of linear pieces. Okay, and there's going to be n pieces. And here these a1, b1, a2, b2, an, bn, these are all just real numbers. a1, b1, so on, an, bn. These are real numbers. And there's one more thing that I want to assume, which is that none of these terms are the same. Right? So I don't have 2x plus 4 showing up twice. Right? So what you might say is that if you look at the set of all of these pairs, ai, bi, right, or I equals 1 to n, right, that these are pairwise distinct. Okay, this is a good mathematical way of saying that no two things are the same as each other. They're pairwise distinct. You know, if I ask you guys what your birthdays are, right, you're always going to say something. Okay? And if none of you have the same birthdays, then the way I'm going to say is your birthdays are pairwise distinct. Right? If you take any two of you, you have different birthdays. Okay? So that's all I'm saying here is that you look at these pairs, ai and bi, right, which is how you can see each one of these linear terms, right? It's completely determined by these coefficients. They're all just different. Okay? And then the last thing I want to assume is that, okay, well, I'm going to write DEG for the degree of a polynomial. Okay? Remember, the degree is the highest power of x. So the degree of the numerator should be smaller than the degree of the denominator. So I'm making these sort of assumptions. Okay, now why do I assume that the degree of the numerator is smaller than the degree of the denominator? Okay. Well, the reason why is, let's say you have something that looks like x cubed divided by x plus 1 times x minus 1. Okay, so this is in the right form, because look, it's a polynomial divided by a polynomial. The bottom is a product of linear factors, which are distinct. Okay. But the degree of the top is a 3. What's the degree of the bottom? 2, right? Because if you factor, distributed this, you get x squared minus 1, so you have an x squared. So that'd be the highest power of x. Okay. Now, if I wanted to fiddle around with this thing, there's a very easy way to do it before you have to do any method of partial fractions or any nonsense. Namely, you can do polynomial division. Right? So remember polynomial division, right? You'd look at x cubed, and you can divide it by, well, this is x squared minus 1. Right? And, okay, you have to remember how you did this. The way I always did it is I add all my extra terms. It's okay. What do I have to multiply x squared by to give me an x cubed? You say, okay, it's an x. And if I do that, I get x cubed minus x. So I get no term there, and I get a minus x here. If I subtract, then, okay, that's a 0, and I get minus x is positive x. Okay, and then, of course, this won't divide into x anymore. So I get a remainder of x over x squared minus 1. Okay? Now, why do we do this? Well, now what you've done is you've taken this fraction, and you have already written it as a sum, right? Right? One of these terms is something nice you could integrate, and the other term is now in the situation where the degree of the top is smaller than the degree of the bottom. Right? And if you think about when you do division, just of numbers, right? When you get a remainder, if you divide by 7, okay, and the remainder is 4, notice that 4 is less than 7. Would you ever get, if you divide by 7, would you ever get remainder 8? No, because then 7 could go in one more time, right? And you'd end up with remainder 1. Okay? So the same thing happens here. If the degree of the numerator is greater than or equal to the degree of the denominator, you can do polynomial division, and you'll end up with, well, a term that isn't divided by the denominator, plus a fraction where the numerator does have smaller degree. So whenever you see polynomial divided by polynomial, if you check the degrees and the top is bigger than or equal to the degree of the bottom, before you do any nonsense like partial fractions, do polynomial division, right? And you break it up. Because now, to integrate this, you actually just need to integrate those things. Right? And these are much easier. Right? This one, of course, you know. And this one, what would you do to it? Do you have to use partial fractions, or is there an easier way? Use substitution, right? U equals x squared minus 1, right? Then du would be 2x, and that x will go away. Okay. So you always want to explore other options before using the partial fractions method, right? Because it's a lot of work. Okay. So, but that's why we have this extra condition here. Right? Is I always assume that we've already done all the polynomial division. Okay. So the statement is, if we have all of these assumptions, right, then there exists, so remember this backwards E means there exists, exclamation point. Anybody remember what the exclamation point means after? It doesn't mean factorial in this case. If I had a number here, it would mean factorial. But there exists factorial doesn't mean anything. So when I write there exists and then exclamation point, this exclamation point means unique. Okay? There exists unique. Okay, so there exists only one. Okay? Or, well, you'll see what I mean in this case. Okay? There exists unique real numbers C1, C2 through Cn, St such that I can rewrite my function p of x over q of x as c1 over a1x plus b1 plus c2 over a2x plus b2 plus cn over anx plus bn. So yesterday, when we did our partial fraction examples, n was 2. Okay? We had a polynomial on top, I think it was x minus 23, and on the bottom we had 2 linear terms, right? Was it x minus 4, or x plus 4 and x minus 5? Okay? And so you didn't have any of this, you just had the first 2 on here. And we were able to find an a and a b on top. Right? So you could decompose x minus 23 over x plus 4 times x minus 5 as a over x plus 4 plus b over x minus 5. Okay? And you'll note that when we went through that method, we saw there was exactly that one set of a and b that would work. Right? There wasn't any choices. We didn't say, oh, well, we can choose an a and we can choose a b. Okay? There was just one way to do it. And what this is saying is that in general, that's going to be the case. If you have these assumptions, then you will be able to find coefficients so that you can break up your quotient of polynomials like this. But that there's only one way to do it. Right? We're not going to prove this. We're just going to take this as a given. Right? So this is, but this is going to tell us that this method this method will work, right? Now, why do we like this method? Well, remember yesterday we showed what happens when you can get your integral into this form. Right? Mind you, these c's are constants. These are real numbers, so they're just going to pull out of the integral. We don't worry about them. Right? And we saw exactly how you integrate these. It just becomes 1 over a, ln of the absolute value of ax plus b plus constant. So this is the power of this method, is that you can break up these rational functions, right, into a sum of fractions, each one of which you know how to integrate. Okay? That's the payoff of all this. See if I have Let's do an example. Is that right? No, I want plus 1. You mess up a sign on one of these and you can make your numbers really bad. Okay, so I have a nice quotient of functions. First, I look to do substitution. Always are looking to do substitution before partial fractions, right? Much easier. But if I do substitution here, I'm thinking, well, probably x cubed minus x. But then the derivative will be 3x squared, and I don't have enough x's on top to kill them off. Okay, so then I say, well, let me see if I can do partial fractions. Well, if I read from the bottom up, I say, okay, I need that the degree of the top is less than the degree of the bottom. Well, the degree of the top is 1. The degree of the bottom is 3. So I'm okay. I don't need to do polynomial division. Fine. Well, now I need to write the bottom as a product of distinct linear factors. Right? So can you factor that into distinct linear factors? How would you factor x cubed minus x? Okay, we'll take an x out. So let's see, we'll just do a little side computation here. So if I pull an x out, then I get left with x squared minus 1. And x plus 1 and x minus 1 exactly. Okay, so I get x, and I get x plus 1, and I get x minus 1. Well, now wait a second. Okay, those are clearly of the form ax plus b. Yeah? A here is 1, b is 1, a is 1, b is minus 1. But what about this x? Is that in the form ax plus b? Well, if it is, then you've got to tell me what a is. 1. Okay, but what's b then? 0. Okay, that's right. Right? So this is it looks like, oh, this is something different, but it's just a very simple case of ax plus b. Okay? So x is included in here. Okay, and we check. They're all distinct, right? These are definitely not the same terms. Okay, and then we add dx to make it a legitimate problem. And what this statement says is if we use the partial fractions method, right, clearing denominators, lifting and separating, we're going to find a way to break this up. Okay, so we try. Okay, now I used C1, C2 through Cn here, just so I label something. But I don't really like to use those letters, so I don't have to. Let me use A, B, and I don't want to use C because we use C too often for constants of integration, so I'll go right to D. So I'll write this as A over x plus B over x plus 1 plus D over x minus 1. Mind you, everything we're doing now is not a calculus problem. Yeah? There's no integral around here. Right? And because we have this formula at the end, we don't really have to do calculus when we get to the end either. Right? So we've turned this into a pure algebra problem. Okay, so first we clear denominators. Okay, remember, clearing denominators meant you multiply by something big enough so that all the denominators of the fractions go away. So here, I mean, it's always going to be this case. You take the denominator of the left-hand side and multiply through by it. And that will clear all of the denominators away. So this tells us 3x plus 1 equals, okay, now when I multiply this denominator by this side, it'll kill the x, but I'm left with the x plus 1 and the x minus 1. So I get A, well, I don't want to write x plus 1, x minus 1. What do I want to write? X squared minus 1, right? Okay. Plus, now when I multiply this by the middle term, the x plus 1s will cancel. And so I'll be left with an x and an x minus 1 on top. But I don't want to write x and x minus 1. I'll write x squared minus x. And then for the last term, right, the x minus 1 will cancel, but I'll be left with an x and an x plus 1. So I'll get d times x squared plus x. Okay, so we clear. Now we lift. Break everything out. So ax squared minus a plus bx squared minus bx plus dx squared plus dx. Okay, so we lift, now we separate. Okay, so let's see. I have, for x squared, I have an a, b, and a d. So a plus b plus d, x squareds. For x, I have a minus b, and I have a d. So minus b plus d times x. And then for constants, I have minus a, and that's it. Okay, what may I conclude about A, B, and D? Okay. A plus B plus D is 0. Why? Well, how many x squareds do you have? 0 on the left, A plus B plus D on the right. So A plus B plus D must be 0. Two polynomials are equal, their coefficients are equal. Okay, so that's the first thing we can conclude. What's the next thing we can conclude? Negative b plus d equals 3. Right? Because, well, we have 3 x's on the left, and we have negative b plus d x's on the right. So 3 must equal negative b plus d. And what's the last thing we can conclude? Negative a equals 1. Okay, so two polynomials are equal if they have the same coefficients. I have a polynomial on the left. I have a polynomial on the right. What's the coefficient of x squared on the right? It's a plus b plus d. What's the coefficient of x squared on the left? That's x. Right? How many x squareds do I have over here? Nothing, right? So, if there's no x squareds on this side, there can't be any x squareds on this side. So this a plus d, b plus d must be 0. How many x's do I have? Well, I have 3 over here, and I have minus b plus d over here. So minus b plus d must be 3. How many constants do I have? Well, I have the 1. Here I have minus a. So minus a must be 1. Okay, so now we need to solve the system of 3 equations with 3 unknowns. Okay? You always need to have the same amount, and part of this theorem is telling you that you will. Okay, so, well, one of these is very easy. If minus a is 1, then a is minus 1. Okay, that's nice. So, hey, we can even write that in already. So, minus 1 over x. That's the first part. I better put the plus so nobody thinks we're cheating. There's another fire drill, for instance, and we had to leave the building. Okay. So, let's see. Then this top equation has an a in it, but I know what a is now. I can just make it a minus 1. And once I make it a minus 1, I can add that to the other side, and I'll get b plus d equals 1. Yep. Okay. If a is minus 1, I add it to both sides, and now I get b plus d is 1. So I know that b plus d is 1, and minus d plus d is 3. So, well, there's a lot of ways you can always work these things. You can add equations together and solve. So, but I always like the substitution method. So from here, this says that what? D is 1 minus b. So down here, I get minus b plus, well, d is 1 minus b. So 1 minus b equals 3. All right, so let's see. I add the 1, I get rid of the 1, so I have to turn that into a 2. And then I have minus 2b's equals 2. So b is also minus 1. Cool. I'm going to put this minus up front. Minus 1 over x plus 1. And d, right, is 1 minus b. So 1 minus minus 1. Which is 2. Okay. So plus 2 over x minus 1. It's just algebra, baby. Okay. Any questions on that? Okay. So now we can rewrite this integral, right, as 3 different integrals. Negative 1 over x dx minus integral of dx over x plus 1 plus 2 times the integral of dx over x minus 1. And now I just use this handy-dandy formula for the integral of the inverse of a, or the reciprocal of a linear function. So, well, we know what that one is already. Negative ln absolute value of x minus ln absolute value of x plus 1 plus 2 ln absolute value of x minus 1. Plus a constant. And as usual, if you're not into the whole expanse, the expansive version, if you want the brevity of a nice, tight, compact version, then, okay, let's see. Those minuses, right, mean quotient. Okay, so you can put them in the bottom. The positive means and put it in the top. And the 2 becomes, you can make that into an exponent. So you get x minus 1 squared over x times x plus 1. No. So that's not too shabby. Not too shabby. Okay, any questions? Well. All right, so let's talk about the second case. The second case is where I do the same thing, only it's going to be much shorter. I erase this middle stuff. I erase all this stuff. I erase those subscripts. And I put up an exponent. Or here, n is a natural number. Okay, remember, this n natural numbers, right? This is 1, 2, 3, 4, 5. So this is much easier to describe, yeah, much shorter rules. So instead of now having all these distinct linear factors, now I'm assuming that all we have is one linear factor repeated over and over and over again. For instance, x plus 1 cubed, right? Or x to the 5th. That would be another one. Right? I'm still assuming that I'm in this sort of reduced form, right? I've already performed all the polynomial divisions I need to. Okay, this is still a smaller degree than the bottom. Okay. So if I do this, well, this doesn't make any sense anymore. Right? How should I break it up? Well, if I break it up and just do ax plus b everywhere, because it's the same term, well, this would be kind of silly, because what would you do if you saw a bunch of fractions with the exact same denominator and you added them together? You just put them into one, right? You'd add up all these constants and that'd be the end of it. So this can't be the way to break it up. And it turns out the way to break it up is the following. You start by just putting the linear term here. And in the second one, you put the linear term, but you square it. And in the next term, you would cube it. And you keep going up, and in the last term, you raise it to the nth power. Of course, this isn't quite as nice as before, because right, our formula doesn't say what to do when you have to square this thing. Right? But that's not so horrible, right? We could probably figure out what's going on, again, just using substitution. Okay, so we'll have to look at that in a second. Okay. But it turns out that, yeah, this is going to work again. If you choose these as your new denominators, then there will exist unique real numbers, C1 through Cn, right, such that you can break up your rational function as a sum of these very nice polynomials. Now, you might be asking, wait. Hold on one second here. We started with a polynomial over a polynomial, and the denominator, right, was just ax plus b to the n. And we didn't know how to integrate it, so we wanted to break it up into partial fractions. And now you've given me all these new fractions, and one of them has the exact same denominator in it. I mean, it was one thing before when we, broke these things up, so we got nice linear terms all by themselves, right? But isn't the whole problem is that we don't know how to deal with these situations? Why are we getting back the exact same denominator? Doesn't that seem kind of strange? Okay, what's the difference? What's the difference? Yeah. I have c to the n. I have cn on top. What makes that different from having p of x on top? It's a constant, right? This is a big difference. Right? P of x, it could be some nasty polynomial. Okay? Cn is a nice, beautiful constant. Status quo. See, you take a calculus class, and at the end, you all want to be conservatives. Okay, well, let's handle this little case of how are you going to integrate these things in the end. Well, yeah. Let's make sure that this is even useful before we start trying to actually do it. So how would we integrate dx over ax plus b to the n? What would you want to do? Well, what u would be not, I mean, what are the choices do we have, yeah? Okay, so let's try it. U equals ax plus b. So du equals a dx. Okay, so, or if you like, dx equals du over a. So this becomes, let's see, dx becomes du over a. So I'm going to pull the 1 over a out. And I just get a du on top. And on the bottom, I get u to the n. Oh, well, that's just u to the minus n, right? We know how to integrate that. Okay, you get 1 over minus n plus 1, u to the minus n plus 1. Right, so 1 over a times, I would probably want to rewrite it as 1 minus n. I hate having my negatives first. Not sure why, but it just doesn't feel right. And of course, we have plus c. Okay, so we know how to integrate these things. There's just a constant. Okay, of course, we pull that out, and now we actually know how to integrate these things term by term. So this really is a useful idea. It's not just a way of making life more complicated. Okay, so let's do an example. All right, so let's try x plus 1 over x plus 3 squared. Wait. All right, we'll just have to set it up. We'll probably run out of time here in a second. Okay, so we check. First, this one I think you probably, it's not hard to see. You can do this by substitution. Is that right? Well, let's see. If you do u equals x plus 3, of course, the du will just be dx. And you still got this x plus 1. But if u equals x plus 3, this is the same as, of course, x plus 1 plus 2. Yeah? So u minus 2 is x plus 1. So you could actually rewrite this as, would this help any? U minus 2 over u squared. And then you could break it up, right, du, as u to the minus 1 minus 2 integral u to the minus 2. Okay, so this one we can do without partial fractions. Okay, but be that as it may, let's see how we would do it with partial fractions. So we want to rewrite this as a over, well, remember, we're going to write down one term for each degree on the bottom. So it's second degree on the bottom. So we're going to write down 2 terms. And in the first term, we write x plus 3 to the first power, and in the second term, we write it to the second power. Okay. Now we have to clear, lift, and separate. So clear, we multiply through by this denominator. And we get x plus 1 equals a. Well, we kill one of the x plus 3s, but there's one left over. And in the second one, we actually kill both of the x plus 3s. So we just get left with a b. Okay, so this is actually going to look out. This is going to look very nice. Okay, we lift. Get ax plus 3a plus b. And separating just involves putting parentheses. Okay, so Hussein, what can we conclude about A and B? What can we conclude? What does this equation tell us? Yeah, you have A here and you have 1 there. So A is, well, we have A here and you have 1 here. So A is 1. What about 3A plus B? Yeah, well, just forgetting about that for a moment. All right, 3A plus B equals, well, let's see, that's the constant term. And what's the constant term over here? 1. Right? So 3A plus B equals 1. All right, but we already know A is 1, so this is actually just a 3. So 3 plus B is 1. Subtract the 3, B is minus 2. Okay. So this tells us that the integral of x plus 1 over x plus 3 squared, dx, can be rewritten as 1 over x plus 3. So I'll write that as dx over x plus 3. Plus, well, actually, it's going to become a minus 2. Minus 2 integral dx over x plus 3 squared. And we know how to integrate these. We actually there's actually a little flaw up here. Nobody caught it, but this isn't always the correct answer. Right? Where is this going to have a problem? When n is 1. Right? So, of course, we already handled that case. That was the case where you have, right, dx over ax plus b. That's the one case of the power rule, right, where you have a problem, right, if you have a negative 1 exponent. Okay? So in that case, of course, you got 1 over a ln absolute value of ax plus b. Okay? So you have to be careful, right, when you don't use this formula for the linear term, right, that you still have to use the ln. So ln absolute value of x plus 3 minus 2. Okay, well, now we know it's actually going to be, well, 1 over a doesn't happen. Then we do 1 over 1 minus n. Okay, 1 minus n here is 1 minus 2, so that's minus 1. So we'll get a plus. And then u, but here the u is, we didn't finish writing the u out, but u is ax plus b, so just x plus 3 to the minus 1 plus c. Yeah. Which is what you'd have expected from the other way that we'd written it out, by the way, when we just use substitution. Okay, so tomorrow we will do some more examples and we'll see how to combine the two different methods where instead of having all distinct or all the same, you can have some distinct and some the same. And we'll also see what happens when you can't factor into linear terms and you have to have quadratics.